So good morning, everybody. We are today in a better condition to enjoy the conferences, and the first one will be given by Albert Cohen. So Albert Cohen, everybody knows him. He's a professor at Sorbonne University, and he is the vice director or assistant director, scientific director of the lab, and so he's recipient of the Popov Prize, and also recipient of an ARC that I think is finished now for a few years. And the talk will be on, I have not the title, tac.
No worry.
On optimal linear and nonlinear dimensionality reduction.
Yes,
yeah,
so thank you. This aimed to be a rather introductory talk. Sorry for those who are maybe a bit bored with the beginning, and maybe in the end there will be some material that is not familiar. Okay, so there will be a lot of common points with what Yvon exposed during his course, but maybe with my personal view, maybe a bit more theoretical sometimes. So linear and nonlinear dimensionality reduction. So let's start from the first concept on dimensionality reduction, which was introduced by Kolmogorov in 1936. So the situation was we work in some Banach space, and we have a compact set, a class, which is typically compact. And Kolmogorov wanted to understand, typically we live in infinite dimensions, so the notion of geometry is not very simple, of volume and everything, so he wanted to understand how to describe the complexity of such class. And the Kolmogorov width, or n width, the concept he proposed is the following. So we call this dn, but it's really dn of k. In the metric x, it's going to be the infimum of supremum. I have to say on what we take the infimum of the supremum, of the distance between any u and a space Vn in X, and the supremum is taking over all the u in the class K. And now, so what is this? This is just taking the distance from u to a space Vn. And now we make a competition between all possible space Vn of dimension n. Right? So it's a very legitimate thing. We have a set. And what we're trying to do is to understand what is a space of dimension n that collectively approximates everyone the best as possible. So for example, this is not a very good set in one dimension. This is obviously a better set. Okay, and that you can, okay, there's connection, of course, with things in statistics like principal component analysis and this kind of thing. Okay, so let me say that the soup, of course, is in fact a max because it's a compact set. This distance, in the case where X is a Hilbert space, is just the orthogonal projection error. And the inf is really an inf. It's not always attained, but you can pretend that it's attained for up to limiting process or things like that. So you can imagine that there is a space that achieves this, although it's not usually easy to find. So the idea was to measure complexity of class, but also to assess the potential of linear approximation methods. So we know many linear approximation methods like trigonometric polynomial, algebraic polynomial, splines, finite element. We want to say how good are these methods doing for a given class of functions. And in order to do so, we want to understand how would be the best possible choice. So let me mention that the classical situation that has been studied, the classical object of study was when K would be the unit ball of another Banach space where Y is compactly embedded in X. That's a very natural situation to consider. For example, X is WSP as derivative in LP, and Y is WTP with T derivative in LP, and T is bigger than S, then you have compact embedding. And then in that case, it is known, very classical result, that Dn behaves like n to the minus t minus s divided by the spatial dimension d. It's a very standard thing, and also it's also standard that classical approximation space will do the job. Good finite element space. So this is essentially reinsuring for classical method. So what's new really there? Why was there a renewed interest for this concept in late years? So what's new there since maybe 15 years? It's first that people began to be interested in classes that are very different, class of parametrized PDEs. Which would be typically of the form U of Y, where Y is a parameter that belongs to some range, which is typically inside some RD or even infinite dimensional. Right? And these classes are usually very different from this. Maybe to give a very standard example. See, can I erase this? Oh, wow. Yeah. Okay. An example that is good to fix the idea. You take the diffusion equation. And you take some boundary condition on some domain. Let's say the domain is a square, and this is a classical setting where you now take the diffusivity to be something that depends on parameters. So, for example, you have here y1, y2, y3 and y4, different diffusivity in the media, and y are these 4 parameters. Okay, so you have a fixed separation, but now you take different diffusivities, sometimes called the thermal rod. And so if you think of this example, now you take all the solution U of y as you vary y. Of course, y has to be strictly positive. Then the first thing you could say is let's, in order to understand what's the Kolmogorov width of this, you would say, okay, maybe we can think of this as a member of a Sobolev space. But this is not a very good idea because of this jump, generally speaking. If you think of this as a member of, let's say you want to measure n width in H1 norm, then all you can say is this is in H3 half because you're going to have a kink in the solution. So if you follow what I wrote here, it would be this simple analysis would just tell you that the width is something is like n to the minus 1/4. Okay. So then there are other ideas, in particular, that say that based on the observation that the dependence of u of y with respect to y is actually analytic, holomorphic. And so a good idea is to say now we're going to take a different view. We're going to approach this thing by a polynomial in the y variable. So we use a sort of Taylor development. Okay. And let's say we take powers less than some k. And then we have very fast convergence of this. And so this tells us that a good space could be the span of this element. So polynomial was called sometimes polynomial chaos or polynomial development. And then immediately, one can see that this is much better now. This is giving you an exponential rate, something like exponential minus constant n to, if you are not very smart, you'll find 1/4, but actually we worked a little bit more on this case with Marcus Bachmeier, and we find really exponential minus n. Okay, so that means that now these spaces are much more efficient, but they are much less standard than the classical spaces. So that's the first novelty. The second novelty is that if you are really after the optimal space, the one that achieves the infimum, again, it's not something which is going to be explicit, but you can emulate this space by some practical realization algorithm that most of you know here, which is the reduced basis algorithm, saying we're going to take Vn as the span of some ui, I equal 1 up to n, and all these ui are picked from k, and they are picked in a greedy fashion. Once you know Vn, you take the new element, un plus 1, as the argmax when u is in k of u minus the projection onto Vn of u. Okay, so of course this is not very realistic. You would have to explore k everywhere. In fact, you are discretizing k. There's all kinds of things swept under the rug. But after you've analyzed all this, the good news is a theorem that we proved maybe 13 years ago with Devor, Petrova, Wojtacik, and others. And it was really improved by Devor, Petrova, and Wojtacik a bit later. That says that the performance of this space are essentially the same as the n-width, namely if dn dk is like n to some power, if the best space behaves like this, then for this particular choice, the reduced basis space will satisfy that the distance of the manifold of the compact set K, to Vn, which is this supremum over K, will also behave maybe with a different constant, but the same power n to the minus s. Okay, that's the the big thing. And it's in a Hilbert space. It's important to notice that this theorem is only valid in Hilbert space. It would be perfectly legitimate to ask similar questions in Banach spaces, but then we have a loss, and we are not fully satisfied. Okay, so that was a recall of things. And I would like to move forward in the nonlinear setting and raise some open question. So the need for similar concept in a nonlinear setting became obvious maybe in the 1980s when people began to think of nonlinear approximation as a way to embrace methods which would be, for example, adaptive mesh refinement, wavelet thresholding, and now more recently neural networks, but you can think of other things where you cannot think of these as linear spaces. Okay? So I want to explain that, first of all, there is no consensus on what is a good notion of a nonlinear width. I will give a few hints, and I will try to explain some framework which I think is illuminating. So the first idea, which would be immediate, would be to say, let's replace Vn by something nonlinear but of dimension n, which means something that depends on n parameters. So typically we think n-dimensional manifolds. Okay, surface is n equal 2, curves is n equal 1. Okay, and let's put the competition on everyone. Okay, so take Vn to be n-dimensional manifold and try to define the same concept, right? And you can immediately see that this is not a good avenue. The concept will be void. Why? Because you can imagine more and more, even when n equal 1, you have to imagine very convoluted objects arbitrarily, and which are going to be more and more and more space filling. So you end up with an infimum which is 0. Okay, so you have just constructed a void concept. And this is telling you, in a way, the problem of that nonlinear approximation can be very wild, and this is what you want to avoid. You want to tame this. So we're going to follow an approach which was proposed by Howard, Devore, and Micheli. What they proposed in 1985, it's already quite a while, was to say, okay, let's tame this concept by avoiding the fact that two elements which are very close would need to be approximated very far on the curve. So insist on the process of approximation, maybe. So I call this the encoding recovery paradigm. So we're going to be interested in having two maps. One map that takes elements from k into n number, and one map that recovers something which is approximately, or hopefully a good approximation. So we call this a recovery map. And this goes to x. And whenever we have the class K, we're going to look at the maximum distortion between an element and its encoding recovery. Okay? And now we're going to infimize this over all possible choice, E and R, satisfying some prescription. We are going to now put some constraints here. And the smallest, let's say the less restricted constraint, which is proposed by Howard and Micheli, is just to ask that these two maps are continuous. Okay? It's not much, but it will already discard this problem. Okay, so I'm going to now draw this on the table. Let's see. Yeah. Where I'm going to ask for some property for the encoding and for the recovery. And the encoding could be either linear or nonlinear but continuous. And similarly for the recovery. Okay, so now if you think of n width, what we explained before, they are actually here. They correspond to say that the encoding could be nonlinear, but the recovery, is linear. So this is where n width stand. Why the encoding could be nonlinear? Because it's what happens when you are in a banner space, because the best approximation is not always a linear operator. If you want everything to be linear, you end up with something a bit more restrictive, which are called the approximation number. Okay, but if you are in a Hilbert space, both are the same. So this is really linear approximation, because the recovery puts you in a linear space. Okay? But we make a distinction when we insist that the encoding is also linear, which is not needed in the case of a Hilbert space because it's really everything is linear. Okay, and now if you simply impose that this recovery and encoding operator are nonlinear but continuous, you end up with something called the manifold width. Finally, what would be the dual situation to the width, the Kolmogorov width, is if you say I'm going to encode with linear information. So it means I'm taking n linear forms, okay? But I allow any possible type of recovery, and we call sometimes this a sensing number. And it's also tied to something called Gelfand width. Okay, so now we have a sort of different options on the table, and I want to mention something which is going to be important for the end of my talk, which is that continuity is very weak, and you feel there's going to be some trouble. I mean, if you want to do numerical things, if you just impose continuity. Although, as I will say, as I will explain, it avoids this problem. So you can introduce something more, a bit more demanding, which I call the stable variance, where you ask that these two maps are Lipschitz. Okay? Lipschitz, so you need to choose a norm on the space Rn. So you impose, in addition to continuity, that E of u minus E of v in some norm is bounded by L u minus v in x. And you want something similar for the recovery. Let's say with the same L. For all possible pair u and v in K and x and y in Rn. Okay, so that gives you a new constraint, and we call this the stable width. It's still nonlinear. And now you see that what's really important, I put L and L here. I could have put two different, but what's important is that the product is fixed, because I can always inflate one and deflate another, and I will not change the distortion. So what's really important is the product, so let's put them equal, and that's what we have. Okay? Right, so they're going to play a game. And you have the choice, and any norm is possible on Rn. You could infimize over all possible norms, but what you want is that this L is fixed once and for all. It's obviously something, it's going to be bigger than 1 in general. Okay, so these are the concepts. And now, how do you compute, how do you estimate these quantities in general? So by above, if you want to estimate this quantity by above, it's usually simple, because what you need is to, is simply because it's an infimum, well, take particular E and R that you suspect are good one. Take particular, let's say good E and R. And of course, now once you do that, you would like to have an estimate by below, and if you have been clever, you might be able to show that what you did is optimal, so to have an estimate by below that match the estimate by above. So by below is more tricky, and I would like to give two vehicles that give lower bound. The first is a topological approach. So the first approach is based on something called Borsuk-Ulam theorem. Which says essentially what? It says if you have a little ball of dimension n plus 1, so you take a ball, let's say of radius epsilon, in a space of dimension n plus 1, and if you take any map f that is continuous onto Rn, what does Borsuk-Ulam theorem tells you? It tells you that there exist 2 points which are called antipodal, u and minus u. Let's call this u star, such that f of u star is equal to f of minus u star. Okay, so it means that any continuous mapping will fail to distinguish between these two objects. And the immediate consequence is if you have some compact set K, as soon as you have such a ball inside, so it cannot be a ball in infinite dimension because it's compact. It's a ball in dimension n plus 1. You have to find a subspace of dimension n plus 1, and now fit a ball, and fit the largest possible ball that is sitting inside. Then you will know that there will always be two opposite points which will be encoded in a similar manner. Okay? So there will necessarily be an error of at least epsilon in the recovery. So it means that, in fact, delta n is bigger than your epsilon. So that's a first strategy. And you see that, in fact, it's a lower bound for everything here. Okay? The second strategy, and now we hear again about Kolmogorov, is based on the concept of entropies, Kolmogorov metric entropies. So I directly define what's called the entropy numbers, which is the infimum over all positive epsilon, such that K is covered by 2 to the n balls of radius epsilon. Okay, so the idea of entropies is, of course, K is compact, so you can always cover. But you would like to compare to understand the compromise between the radius and the number of balls. Okay, you can relate this notion to encoding, because you see you have 2 to the n options of centers that are close to up to this quantity of any one. So it means that with n bits give you 2 to the n possibilities. N bits encoding has precision epsilon n over K. So why is this giving you a lower bound? Because you have something called Karl's inequality. That tells you it's a little bit very similar in flavor to the wording of the theorem on reduced basis. It tells you that if dn, the n width, decays like n to the minus s, then epsilon n will decay up to constant, a different constant like n to the minus s. So that's Karl's inequality. And it essentially tells you everything that you can approximate by n number in a linear way, you should be able to approximate by n bits. You should have to be able to encode cleverly these bits, these numbers, and reach the same decay. Every one of you, I think, can easily prove Karl's inequality if you accept to lose a log factor. The difficulty is to have exactly the same rate. So I consider this as a lower, as an estimate by below, because if you know that the entropy do not decay very fast, then it means that the n cannot decay very fast. But now, does Karl inequality work for this other thing? So it's interesting. Karl's inequality is not satisfied for delta n, but works for the stable variance. Okay. So it's a good sign that it's because you know everything here is related to encoding. The fact that you can encode things by bits means that you have a certain stability, and it's a good sign that it's a reasonable method. Okay. So now, okay, if you look at this, you could say, okay, this is strange because in fact I got a lower bound, but it's the same lower bound, for example, here for all these quantities. Okay? So how am I going to prove that in certain instances nonlinear approximation, nonlinear width are significantly better? I would need to prove something really that the lower bound is much worse for the linear methods. How is this going to work if I have in the end something very the same lower bound for everyone? Okay? And this is a remark I want to make now. The big difference between linear approximation and nonlinear approximation has to do with convexification. So let me make the observation that implicitly, when you compute this linear quantity, you convexify. Why? Because you can see immediately, for example, if I take dn, that dn of k is exactly the same as dn of the convex hull of k. Why? The convex hull of k is larger than k. But obviously, if I can approximate two elements by a linear space at a certain accuracy, then they have some. I can approximate by the same linear space with the same accuracy just by triangle inequality. Okay? So what it means is that really when you look at the n width of this, you're actually looking at the n width of this. Okay? And that means that this ball, when you compute by a lower bound by the Borsuk-Ulam techniques, you should really not fit a ball here, but you should fit a ball here. And this is much worse. Okay? And of course, it's not the same for nonlinear things. Okay. So I would like to now go to maybe more advanced material. And first, I would like to say that the big, to me, one big problem in all this, and maybe it's too wild of a problem, is to achieve the equivalent as these practical realization algorithms for these quantities. I mean, to attain, so that would be to me the Graal, to have strategy which are, if you think about it, learning strategy, because what you are doing here is really exploring the space K offline, and you try to explore it in a clever way, and learn as best as possible the best possible space. So now, you see, for example, practical realization, I must say, are difficult, are not something that you can easily understand for these other notions. So, for example, to me, it would be very interesting to have strategies that determine in a greedy fashion the best linear forms, the best coordinates in a way to characterize the space K. This is a totally open problem to my knowledge. And it's strange because you would say this is a sort of dual situation. In fact, there is an interesting result that if you were in the situation that I erased, where these balls are, this K is a unit ball of another space Y, actually it's an interesting duality theorem that tells you that the sensing number of the Gelfand width of y in x is the n width, the Kolmogorov width of x in x prime in y prime. That's a duality theorem, but very tied to unit balls. So you would say, okay, this is just changing, passing to the dual. But in fact, for the type of situation that we are considering, it's not at all going to help you. Okay? So I would like still to show that there is, in theory, an approach that will exactly reach the manifold width. I'm going to give you an algorithm in a way, but it's an algorithm on paper, not at all. But it's going also to make a nice connection with the Kolmogorov entropies. And essentially, it reached me to the conclusion that the main concepts were already here. They are the Kolmogorov width and the Kolmogorov entropies. Kolmogorov had understood everything already. So the theorem is the following. It's a theorem we proved about 2 years ago with me, Ron DeVore, and Gergana Petrova, and Przemek Wojtacik. It says the following. So it's again when X is a Hilbert space. It says that, if you look at the entropy number of K, then they dominate the stable width if you accept to lose a constant here. And so if you think of what is this is a bit reciprocal to the Karl's inequality, because I told you that the Karl's inequality also works for delta NL. Okay? To be precise, I think that if you want L equal 2, you can get it with a constant C here, which is 26 or something, but you can certainly improve. You can put L as close to 1 as you like. Okay? And so what does this? So again, if you're combining with Karl's inequality, it tells you that the asymptotic decay of epsilon n is exactly the same as the asymptotic decay of delta NL. It's very interesting. It means that the two concepts are essentially very similar. It tells you also there are other consequences to that about the transport of complexity, another consequence, about mapping in infinite dimension. If you have some compact set K1 in some space X1, some compact set K2 in some space X2, and you look at a certain mapping F, nonlinear mapping, you are interested, of course, in understanding if K1 has a certain width, does K2 has a certain width? Does the reduction of complexity is transported? So we had a result on linear width, which was not very satisfactory, but interesting, that says that if F is holomorphic, then if dn of K1 decays like n to the minus s, then dn of K2 decays like n to the minus t for any t bigger than t smaller, sorry, than s minus 1. There was a little loss there. That's something we had proved using polynomials ideas. But now if you accept this result, there is an interesting consequence that if F is just a Lipschitz map, then delta, you have the same result, delta NL of K1 decaying like n to the minus s will imply that delta n L of maybe a different L of K2 is less than n to the minus s. You receive the same rate. So Lipschitz are very good, Lipschitz maps work very well, and this is definitely because of this thing, because you're going to use covering, and of course by a Lipschitz mapping, a covering becomes a covering in the new set, because you have contracted norms. Okay, so it means that nonlinear approximation is much better in a sense of not imposing as much on the mapping. So I'm not sure I have time to explain in a few lines. Do I have 5 minutes or 3 minutes? Ah, okay, wonderful. I could tell now. Okay, so I'll explain the proof because the proof is interesting. It contains a strategy, a concrete realization, but you will see it's a very paper-like concrete realization. So the proof is the following. You start from your epsilon n. You say, okay, let's say you have epsilon n, and you want to prove something about this. So you begin by taking a covering by 2 to the n ball. So you have I equal 1 up to 2 to the n. And you have balls of radius epsilon n, so epsilon will be epsilon n, that cover K. That's the situation, okay? And now we want to make an encoding-decoding. How do we do that? Well, we use something from Banach space geometry. Actually, it's very Hilbert space geometry, called the Johnson-Lindenstrauss lemma. So we're going to use the Johnson-Lindenstrauss lemma. What does the Johnson-Lindenstrauss lemma says? It's very well known, for example, to computer scientists. It tells you that when you have points in high dimension, when you have 2 to the n points, you can project them, you can linearly map them onto a space of logarithmic dimension. So if you have 2 to the n points, you get to constant times n points, and preserve essentially distance. So there exists a linear map with rank of L less than Cn, okay, such that L ui minus L uj is less than 2 ui minus uj and bigger than, let's say, 1/2 of ui minus uj in X for all I and j. Okay? So you could replace 2 and 1/2 by 1 minus delta, 1 plus delta, but this would change the constant C. So this, I tell you. And they say L is, by the way, linear. Okay? So we're going to use that to encode. But so far, it means that you can encode this ui, uj by n, by something which is in a space of dimension n, okay? By n number. Okay, so that gives you an encoding, but I still have to say how this encoding has to work everywhere, not only on this UI, uj. Okay? And so that gives you also decoding, because this is completely injective. Okay? If you look at L from this net of points, let's call N the net of all these UI. Okay? L between N and L of N is completely bijective. Okay? So there is a right inverse, which I could call let's say B. Okay, that's my bijective return. Okay, what do we know about L? L is Lipschitz with constant 2, and B will also be Lipschitz with constants 2 because of the lower inequality, but so far this is only between these two spaces. Okay? So what we're going to do now, so both L and B are two Lipschitz. And now we are going to use this mapping to define E and R everywhere by applying a theorem called Kirsch-Brown theorem, which is an extension theorem. So what does Kirsch-Brown extension theorem tell you? It tells you that if you are in a Hilbert space, once again it's very important to be in a Hilbert space, if you have mapping which are Lipschitz defined on compact set, obviously N is a compact set, it's a finite set of points, okay? And L of N also, then you can extend this mapping into a Lipschitz mapping with the same Lipschitz constant. So you will extend L into E, and you will extend B into R. So once you have done that, it's a one-line thing to show that these new these operators now will satisfy what you want. I think I have room to put it here, because what do you do now? You take any U in K, and you look at U minus R of E of U, and you insert its closest point, UI. U is close to some UI at rate at accuracy epsilon n. So you put U minus UI. And by triangle inequality, you have UI, you have R, UI minus R of E of UI, but UI is the same as R of E of UI because the reconstruction is exact on the net. And now you apply Lipschitz constant here. Lipschitz constant 2, Lipschitz constant 2, so you have 4, so you have 5, U minus UI x, and this is less than 5 epsilon n of k, right? Very not difficult, but you have to use results that are super tied to Hilbert space. Let me tell you also one thing. There is something misleading in this thing. It looks like the encoding is really a linear map. And this is not true. I was completely... So if it was true, then it would mean that you would have the result for sensing numbers, because you would have encoded... Oh, sorry. So it is not true, because in the Johnson-Lindenstrauss lemma, it's not really a projection that you do. It's a rescaled projection, with a huge, huge, huge number, but it's only behaving well on this set of points. So it's very critical that you do not extend L as a full L. You have to extend it using this Kirsch-Brown theorem, and it's not very constructive, but at least it gives you an idea of what's going on. So I'm done. So my conclusion is really that the right concept to me here, the fundamental concepts are the width and the entropies, and there are still all kind of open, challenging questions. Maybe this is too wild as all kind of restriction may lead to more interesting results, maybe. So I thank you.